In this lecture video, we'll be talking about using matrix or linear algebra methods for quantum mechanics, for solving quantum mechanical problems. So the motivation here is that we want to move beyond these simple systems like the hydrogen atom or H2 plus or helium, or even the simple diatomic molecules that we discussed already. However, as we move to these systems, there's a lot of moving parts, and so the equations can get rather large. And so we need to develop some tools to help manage this additional complexity, and we're going to develop essentially another level of abstraction, another way of representing the various mathematical operations that represent the behavior of particles in our system and their properties. So we're going to use linear algebra or matrix methods for this system. To look at all these systems. And the advantages of this approach is that we can still, by adding this additional sort of level of abstraction, we still maintain a lot of the features of the sort of symbolic algebraic and calculus based approach that we've been using so far. So we maintain a lot of that and the sort of power of those approaches in terms of representing what's happening in the system. But we can also, of course, feed results to a computer if we need to, or if it makes sense in a particular case. But we can switch back and forth, so we're not really giving anything up. We're just adding another tool. Also, these matrix representations of the systems are are useful as tools for describing and designing various computational quantum mechanical methods that are widely used in chemistry. So we start with something called the secular equation, or the matrix Schrodinger, the matrix version of the Schrodinger equation. And it starts with something that we're familiar with and that's been a recurring theme in this course, which is the superposition principle, that we can represent the wave function of a system. Say it could be a fairly complicated wave function, and we can represent it as a sum or linear combination, a sort of weighted sum of other functions. They could be, say, eigenfunctions of a simpler Hamiltonian. They could be things like sines and cosines, or it could be a polynomial, something like a Taylor series, Taylor-Maclaurin series, that sort of thing. And we want to solve the Schrodinger equation, which is h psi equals e psi, where I've used a capital to indicate that we have a sum of sort of simpler lowercase psi wave functions. And then the question is, how do we solve this somewhat more complicated Schrodinger equation that involves a sum? And the answer is that we can convert this to a matrix equation. And so first, let's define a Hamiltonian matrix. And of course, anytime you have a matrix, essentially you're defining that matrix by coming up with an expression for the various matrix elements. So each of these matrix elements is going to involve an integral of the Hamiltonian um, sandwiched between two of these wave functions, these basis functions, the individual psi I or psi j that make up our uh, that are make up the sum that gives us our wave function. And so our individual matrix elements hij are equal to the integral over all space of psi I star h psi j d tau, where d tau is the um, generalized volume element. And so that's going to be true for each of these matrix elements. So our Hamiltonian matrix, where we'll represent Hamiltonian matrix with a capital H with a tilde or tilde above it, and it's going to look like this. It's going to have all of these different elements. Those are going to be presumably numbers, or maybe some symbol like alpha or beta or A, B, or C or something like that that represents these various integrals. So we have a sort of table of integral results here. Meanwhile, okay, our wave function is represented since the true underlying wave functions are represented inside these integrals that go into the various matrix elements, then what's left over are these linear coefficients. And so we're going to take those linear coefficients and place them into a column vector. And so we'll call that psi with perhaps with a dagger over it, or maybe a boldface psi. That's what I use in the notes. And that's going to be some column vector containing all of the linear coefficients, C1 through Cn, where capital N just represents the number of different basis wave functions that are in our superposition principle. So we've got the underlying wave functions that form the basis set. Those are built into our Hamiltonian matrix. We have the linear coefficients. Now we have all of the pieces specified, and we can represent our Schrodinger equation as a matrix equation as follows. H tilde psi equals E psi. And this is, it can be shown. I'm not going to go into a lot of detail here, but of course it can be shown, and it should seem somewhat intuitive that this is essentially another way of representing the Schrodinger equation. It looks like the Schrodinger equation, has all the same elements, and it turns out that it works, right? So so our H tilde there is our Hamiltonian matrix. Our psi is a column vector, and then we get that acting our matrix on our column vector, or multiplying the two together, gives you back some energy, which is a scalar quantity, times the column vector that we started off with. So if we want to think about this in terms of a matrix multiplication problem, it looks like this. You have this matrix here on the left, this big square matrix, and then we perform a matrix multiplication onto this column vector, and then that gives us back some energy times the column vector that we started with. And so this is the matrix equation that we need to solve. And this is often referred to as a matrix eigenvalue equation. Okay, but you can also think of this as something that you may have run into in pre-calc, where you have a system of coupled linear equations, and you need to solve that system of linear equations. And like in that case, the basic solution is a determinant method. So we set the determinant of the Hamiltonian matrix minus E times I, where I is the identity matrix. And we can think of I as essentially, it's going to be a matrix that's diagonal and has ones all the way down the diagonal. Like for a 3 by 3, the identity matrix would look like that. Then we set that, we evaluate that determinant, right? And then we set the determinant equal to 0. And then the first step is we solve for the energies or the energy eigenvalues. Typically, you get 2 or more. It often depends on, of course, the rank of the matrix. You're going to get, for a 2 by 2 matrix, you're going to typically get 2 energy eigenvalues, although they could be degenerate. You could have 2 of the same value. And for a 3 by 3, you would get 3 energy eigenvalues, and so on. Anyway, so then we plug, then after we get our individual energy eigenvalues, let's label them E sub n, where little n there is the, I guess I could have used, little n is some number that's between 1 and big N, which is the rank of the matrix. So we plug that E sub n value into the matrix equation to get back the individual C sub I values, the individual linear coefficients for that state psi sub n. Okay, and again, that determinant we can see looks a little bit like this, right? So we've got the vertical lines indicating the determinant, and down the diagonal, all of the terms look like h11 minus e, or h22 minus e, and so on, down to hnn minus e. And then all the other matrix elements are just the h sub row column, so h12, h21, and so on. So when we evaluate this determinant, this is going to give us a polynomial in E, and then we have to find the roots of the polynomial, and those roots will be the energy values. So let's look at a simple case, and of course we'll return to this two-state case in more detail later. But if we just look at sort of a general determinant for a two-state case, we're going to have h11 minus e in the upper left-hand corner. In the lower right corner, we have h22 minus e, and then off the diagonals, we have h21 and h12, and we evaluate that determinant and set it equal to 0, and that's going to give us h11 minus e, right? So we use the typical method for evaluating a determinant. That's going to give us h11 minus e times h22 minus e minus the product h21 times h12. And again, we set that all equal to 0. We distribute, using the FOIL method. We collect the various terms, and in terms of the various powers of e, so there's going to be an e squared term, there's going to be an e to the first power term, and then there's going to be other e to the 0 power terms, or just constant terms. And we plug those into a quadratic equation, and then we get a result. In this case, we're going to get 2 energies. It's going to be in the form E equals some number plus or minus some other number. And then, of course, we plug each of those in turn back into the matrix equation to solve for the individual linear coefficients to get what the eigenvectors are for the system. In other words, an eigenvector being that column vector that represents the linear coefficients of the state of the system. And similarly, you plug in the other energy eigenvalue to get the other state in the system. So there's going to be, for a 2 by 2 matrix, there's going to be 2 possible states, and they're going to have potentially different energy levels, and they're going to have two different wave functions. Another thing is that we get, we will find that the wave functions, the wave vectors are going to be orthogonal, but mathematically it looks a little different. Um, if we have two states, say psi A represented by this column vector and psi B represented by this other column vector, so we have psi A is essentially a series of numbers, A1, A2, dot, 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 down to AN, and psi B is B1, B2, dot, 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 down to BN. And we need another piece, which is we define the adjoint, or psi A dagger, as a row vector where we've put in all of these same individual elements of the column vector, but we've rearranged them into a row vector, and we've taken the complex conjugate of each of those. Of course, if they are real linear coefficients, then the complex conjugate is just the same as the real number. But if it's complex, then we'll have to replace all instances of I with minus I in those potentially complex linear coefficients. So that's the adjoint. So then if we multiply the adjoint of our wave vector psi sub A with psi sub B, then of course that's going to be equal to this kind of multiplication of a row vector with a column vector, which is essentially just a sum. And so it's equal to the sum of AI star BI. In other words, A1 star times B1 plus A2 star times B2, and so on. Now, if the result of that sum over all of those linear coefficients is 0, then we say that psi A and psi B are orthogonal. And thus they represent different states. They have different properties, perhaps a different energy, although they could be degenerate. So we've represented our Hamiltonian as a matrix. We've represented our wave functions of the system as these column vectors. Again, the underlying functional form of the wave function is still buried in this representation, right? It's in these integrals, right? So we've represented the underlying basis set or set of functions for our system in terms of the individual integrals that go into the Hamiltonian matrix. Anyway, so we've represented our Hamiltonian as a matrix. We've represented our states as these column vectors, and they can also be row vectors if we take their adjoint. And it turns out that this is also true of other operators. So things like position, momentum, angular momentum, any angular momentum along a particular axis, spin, these can all be represented as matrices. Now the form of that matrix is going to depend on the basis set used, in other words, the underlying sort of wave functions, and you end up with a matrix defined very similarly to how we defined the Hamiltonian matrix previously. It essentially involves defining the various matrix elements in terms of integrals over the operator sandwiched between two different wave functions. And there are some interesting properties of these operators, which is that operators that represent observables In other words, things that we can measure about the system, things like position, momentum, energy, dipole moment, things like that. Those kinds of operators have some interesting symmetry properties, and we could say that they are Hermitian. And that just means that they're also called self-adjoint in that, so if we have some matrix representing an operator, we'll call it M, it would be equal to, let's fix that. That it would be equal to its adjoint. And this is a symmetry property of matrices. It's a concept from linear algebra. You can have Hermitian matrices. It's one of the ways that you categorize matrices when you're working with various linear algebra problems. And Hermitian matrices have certain properties that will dictate, what kinds of methods, linear algebra methods, one would use. In the context of quantum mechanics, this is also a property of these operators that represent observables, and that terminology is borrowed from linear algebra. Well, that's all I want to say about the secular equation. Next, we'll work on applying the secular equation to some two-state problems, and then we'll move on to some other problems involving these methods.